purpose of this lab is to capture and analyze the motion of a real-world object moving horizontally at constant speed and comparing it to a computational model of the same experiment. Using Newton's first law, the position update formula, and the velocity update formula derived from Newton's second law, the results show that the computational model closely aligns with the results observed in the real-world experiment when both results were graphed side by side. In the real-world portion of this experiment, a wheel was rolled across the counter at a constant speed and was videoed. The wheel, being the system, weighed 0.129 kilograms and was 0.195 meters in diameter. The surroundings of the experiment was the counter, the air, and the rest of the environment. The origin of the axis was set to the middle of the wheel, and the position of the wheel is always considered to be the very middle of the wheel as well. The wheel initially at t equals 0 starts at an x-coordinate of negative 0.003943 meters, and since this experiment has to do with only the horizontal axis, y and z are irrelevant. The wheel had been pushed off screen, and in the video rolls on screen for 1.835 seconds. For each frame of this video, the wheel's position was plotted, which was always the middle of the wheel. Here's a demonstration of this. You see the position of the wheel is always the middle. In our computational program model for our experiment, a ball represents our wheel and has the same mass of 0.129, has the same starting initial position at t equals 0, and has the same velocity of the wheel we just calculated. Over the course of 1.835 seconds, the ball's velocity is updated using the velocity update formula because it includes the net force and the mass and the delta t, which we know, and we know the net force is 0, so this would all cancel out, and we know we'd have a constant velocity. And because we have a constant velocity, it makes it very easy to use the position update formula, this here, to update the ball's position as well. We plot both of those on a graph, and it also prints out the time and the ball's x position to be used on a Excel sheet. If you plot both the experimental position data and model position data onto a position by time graph, you'll see that they're both linear. Position changes over time linearly. Why is this? It's because there's no force acting on the system. And as you remember from earlier, this formula, the velocity update formula, because there's no force acting on the system, all this is zeroed out and velocity is constant. And because velocity is constant, the change in x over the change in time is always constant and linear. Now, you may notice that the experimental position line is lower than the model position line and has a higher velocity. This may be due to because the model position didn't account for friction or air resistance. Also, the camera angle can affect how the position was plotted. What if instead of having the wheel go in the negative x direction, we instead had it go in the positive x direction? Well, if that were the case, then this would be 0 and position would be increasing as it goes up instead of decreasing as it goes down. And the lines would look a bit more like this because position is increasing as time goes up. Is it possible to state how many pushes and pulls are added together to give 0 net force in the experiment? Well, because the force of the push was applied only instantaneously, it's not part of the net force. The only net force canceling each other out would be gravity and the force of the table pushing back up onto the wheel.